giant dinosaurs, Earth was covered with giant insects. Imagine a world where dragonflies are the size of crows and millipedes are as long as cars. Welcome to the Carboniferous period. This period was one of the most transformational periods in the history of Earth. The planet's land masses were beginning to form the supercontinent of Pangaea. Extensive swamps and warm, humid forests dominated the landscape. And giant insects weren't the only huge creatures roaming the planet. There was also a vast array of marine life, like early forms of sharks, and a giant amphibian that would reach up to 6 feet long.
This thing saves us money.
Thanks.
300 million years ago, and dive into the Carboniferous Age. You'd probably notice would be the giant insect-like creatures. One of the most iconic was the Meganeura. This insect resembled a modern-day dragonfly, except with a major twist. It had a wingspan of up to 75 centimeters. Yeah, scarier than that, though, it was carnivorous, hunting down other insects and small amphibians. Hopefully it doesn't come for you. So that thing is in the sky, but on land, you'll have the Arthroplura. This millipede-like creature could grow up to 2.5 meters long. Luckily, it wouldn't go after you. It preferred munching on decomposing vegetation. Hey, before we talk more about these giant insects, there's another giant issue we need to worry about, and that's our planet's ecosystems and how important it is to help them. The creepy-looking insect was the Pulmonoscorpius. This was a giant scorpion that mostly roamed the swampier areas of Earth. They could grow 70 centimeters long. There were also giant cockroaches that grew to 10 centimeters, and mayflies with 45-centimeter wingspans. So it's safe to say that you have a lot to watch out for when you're wandering around in this period, but the question is, how did these insects get so big anyway? You may have noticed as you've been hanging around in the Carboniferous Age, you feel a lot more energetic and alert. Maybe you've had an easier time running around. This has to do with the oxygen levels in your current world. Researchers estimated that the atmospheric oxygen levels were as high as 35% during this period. Compare that to the 21% we breathe today. Oxygen was one of the key factors in the gigantism found in insects at the time. But why would this make them so giant? Insects breathe differently from other creatures. Insects don't have a circulatory system to transport oxygen. Instead, it gets delivered directly to their tissues through a network of tiny tubes called the trachea. And the more oxygen in the atmosphere, the bigger these insects are. But there might be more reasons why the insects grew to this size. Another theory suggests that the insects were forced to grow so large due to oxygen toxicity. Yeah, as amazing as oxygen is, you can have too much of a good thing. Too much oxygen in your body can create what's known as free radicals. These are unstable molecules that can damage your cells and even damage your DNA. In the case of our insects, they were forced to grow this big. Otherwise, they'd suffer oxygen toxicity. Growing larger would slow down the rate of oxygen absorption, making it harder to suffer from too much oxygen. And the same could happen to you. The longer you hang out in this period, the higher oxygen levels will cause you to experience nausea, respiratory issues, and even some effects on your nervous system. Now, insects were arguably the stars of this age, but they weren't the only things to experience massive change during the Carboniferous period. This time was known as the Coal Age. That's because of the extensive coal beds that formed after ancient forests decayed. These coal beds are one of our main sources of energy. We're still using them today. And a lot of the fruits and veggies you find in the grocery store may be descendants of plants from over 300 million years ago. The Carboniferous period saw the evolution of the first seed-bearing plants, creating more diverse ecosystems than we've ever seen before. Wait, what's that over there? Kinda looks like a dinosaur. Oh, hey, little guy. Turns out this wasn't a dino, just one of the first reptiles to ever appear. But if you stick around a couple of million more years, we'll enter the Mesozoic era, which was known as the Age of Dinosaurs. Speaking of change, the atmosphere was another part of Earth that evolved during this period. Earth had a lush, greenhouse-like climate when you first arrived, warm and humid temperatures to support the swampy forests we've been mucking about. But as the period progressed over millions of years, the climate transitioned to what's known as an icehouse Earth state. The temperature would get significantly lower and ice sheets would begin to form, mainly in the southern hemisphere.
As we go into the Carboniferous, there was once again a power vacuum in both the marine and terrestrial environments all over the world, for two totally different reasons. In the ocean, life is bouncing back from the death of the armored fish and many other dominant groups. And on land, the spread of the massive global forest would open up new opportunities for those who were able to adapt. This forest would become so all-encompassing that not only would it have a very unique effect on our planet and its inhabitants at this time, but it would even affect our modern world in a critical way, which is wild to think about considering this period began 358 million years ago. I've been looking forward to this one, so let's dive into the Carboniferous jungles. Carboniferous, the world was undergoing more drastic changes than ever before. Gondwana was slowly drifting northwest on a collision course with Euramerica and Siberia, and the small chain of islands that started to form to the northeast of the supercontinent during the Devonian had grown into a small landmass in its own right. It's impossible to tell from looking at it, but this small island continent will one day make up part of China. The formation of this landmass further isolated the Panthalassic and Paleotethys oceans from one another. But the real massive change was when this little blue and brown marble finally started to change into a blue and green marble. Plants, fungi, cyanobacteria, and a few animals had been able to establish themselves on land in some capacity leading up to this time. But generally speaking, the first pioneers were restricted to staying close to the waterways. But this was all about to change, because in the hot, humid climate of the early Carboniferous, there was about to be an explosion of biodiversity every bit as impressive as the Cambrian or Ordovician explosions that we saw in the oceans of the past. And the first organisms that we see this with would be the plants. Horsetails, club mosses, ferns, primitive conifers, and cycads all get their start here. And that's just the ones that we're familiar with today. This jungle would spread out from the rivers and ocean and cover the entire globe in an endless tree line unlike anything we've seen up until now. And this would have a profound impact on the world in several ways. For one thing, the presence of all this plant life also meant a massive increase in oxygen. And anytime that we see big changes in the air, usually that makes for big changes for everything else, as we've seen before. For one thing, it started to change the climate. We start to see a cooling trend by the middle Carboniferous that leads to an ice cap forming at the South Pole for the first time in millions of years. Probably the only part of the land that wasn't covered in vegetation. As this runaway effect continued on, generations of plants would come and go, and old vegetation would fall to the forest floor. Either just through natural processes, or much more likely forest fires that would be taking place as an extra consequence of all the oxygen in the atmosphere. And these plants spent their entire lives taking in CO2 and expelling O2, leaving the C, or carbon, locked in their tissues. And over the 60 million years of this period, this would be something that would be locked away in the earth forever. So slightly off topic, this is something that I hear from people all the time. People who say the use of fossil fuels means that we're using the liquefied fossil remains of dinosaurs are pretty much dead wrong. The overwhelming majority of the fossil fuels in use today originally are dated back to the coal beds of this time, 100 million years before the first dinosaur ever existed. In fact, there's so much carbon in the deposits all over the world from this time that this is the inspiration behind the naming of this entire period, the Carboniferous. Checking back in with the oceans.
Puzzle?
Or the state that it was kind of left in by the end of the Devonian was pretty sad. But of course, as always, extinctions leave opportunities open for the survivors to expand into new forms. And in the warm waters of the early Carboniferous, there was about to be another mass diversification. Echinoderms, cranoids, gastropods, and bivalves all managed to pull through. And the cephalopods were still hanging on as well, but by now the straight and curved-shelled varieties had died out. What was left was the ammonites and the true nautiloids, which, despite animals like the modern nautilus bearing a resemblance to ammonites, this is how far back the two groups actually separated. The trilobites were still around, but unfortunately, they were definitely on the decline compared to previous periods. They may outcompeted by other forms of arthropods like the true crustaceans. This seems to mark the end of the invertebrates' reign as the rulers of the oceans, as the fish, despite losing 96% of their biodiversity by the end of the Devonian, were about to take control for themselves, and this time it would be in a much more familiar form. This was the Chondrichthyans' time to rule, the group of fish that, among other things, would lead to the shark. Now, this line of fish has been around since all the way back in the Silurian, but they had remained smaller and relied on their cartilage-based skeletons to allow them to be faster and evade the armored monsters that were filling the dominant roles. But now, after the fall of the Eurypterids and placoderms, It was a perfect moment for them to become the masters of the sea. The Chondrichthyans radiated into several different groups, the most successful being a different group from the true sharks called the Eugeniodontids. These creatures had some very interesting face and headgear, but otherwise, a lot of them were starting to be very similar to modern sharks. For example, there's the early species called Cassiotis. This was one of the basial members of the group, and although they would survive for quite a long time, it would also give rise to several other noteworthy creatures, like the slightly more unique Ornithoprion, which in itself would be the direct ancestor to probably the most well-known member of this order in the future. The fish quickly bounced back as the Carboniferous went on, some groups even managing to spread into freshwater ecosystems, putting them in close proximity of the new world opening up in the air above. And this world would be a world of swamp monsters and giant bugs. As oxygen levels skyrocketed and the land was covered in tropical forests and swamps, the vertebrates and arthropods were about to take their age-old evolutionary arms race to the new frontier. It was at this time that some of our tetrapod ancestors started to become true amphibians, finally developing the fins and fin-like legs into proper weight-bearing limbs. The earliest example of this was with a creature called Peterpes, a name which means Peter's foot.
Who's Peter?
This 1 meter long creature is very important because it's currently thought to be the evolutionary link between the tetrapods that were more similar to lobe-finned fish and the true amphibians. And also because fossils of land animals from the early Carboniferous are extremely rare. So for all we know, there might have been a ton of other animals like this crawling around. But as time goes on, we do see a lot of other strange types of amphibian in the later stages. Some of them even had their shiny new legs shrink and become more snake-like, like this thing called Coloraderpatin. And then someone in the opposite direction, and further develop their limbs for walking on land, like Tuditanus. And we even have some major predators coming from this group, like Anthracosaurus, measuring up to 3 meters long, and is also known as the reptile-like amphibians. But the was a group of ruling amphibians called the Temnospondyls. Large species like Eriops may have grown up to 3 meters long and 200 kilograms, probably hunting somewhat similar to, once again, crocodilians. These were some of the most powerful vertebrates on the land. But unfortunately, not only did our arthropod competitors have a head start colonizing the land, but the way that they were designed was going to give them an edge in this high oxygen environment. You see, unlike terrestrial vertebrates which have 2 lungs and breathe through their nose and throat, terrestrial arthropods have openings across their bodies that connect to the tissues that need oxygen. That's why today there's an upper limit to the maximum size that arthropods can reach. Because in today's atmospheric oxygen level of 21%, bugs can't grow to 3-4 meters long. But if you crank the oxygen up to, say, 35%, as it was in the Carboniferous, suddenly the limit has been raised. In these jungles, there were giant bugs, like the terrifying 70-centimeter long Pulmonoscorpius. Yes, this was a scorpion the length of a human arm, the largest any terrestrial arachnid would ever grow. And we also see the largest land invertebrate to ever exist, the herbivorous Arthropleura, a millipede that could grow up to 2.5 meters long. And the bugs would even take to the skies for the first time during this period, most well known of which being the falcon-sized Meganeura, a relative of modern dragonflies and damselflies. And among all these monsters in the tropical landscape of the Carboniferous, there was even a relic of a bygone time lurking in the swamps, the 1.5 meter long Campiocephalus, the very last of the sea scorpions. Despite this guy's pedigree for predation, the Eurypterids' days were long past them at this point. Basically nothing more than an oversized horseshoe crab, probably using its shovel-shaped body to push through the muck and scavenging on whatever it could. A humble place for many of the smaller vertebrates running around. Our direct tetrapod ancestors were constantly having to hide from giant carnivorous amphibians and bugs.
You think oxygen is pretty great? Of course you do. But what if I told you there was a time when oxygen almost wiped out all life on Earth? This is the story about how too much of a good thing can ruin everything for everybody. Years ago, in the Archean Eon, when the world was a place you'd never recognize, or even be able to survive in. Back then, only 2 or 3% of the planet's surface was dry land. The rest was covered in oceans, and they were full of iron. Because of all that iron, the oceans were probably not blue, but green, and not because of algae or other life, but because of rust. You might think of rust as being brown, but green rust is a thing too. It forms where there's a lack of oxygen, and back in the Archean, oxygen was in short supply everywhere. So in the oceans, iron reacted with hydroxides and elements like sulfur and chlorine, covering much of the world in green rust. Above the green oceans, the atmosphere was mostly nitrogen, as it is today, along with water vapor, carbon dioxide, and methane. But again, very little oxygen, which was fine at the time because microscopic life on Earth back then was probably anaerobic. Then, about 2.8 billion years ago, some new kids showed up, photosynthesizers, but not the kind that we're used to. These were bacteria, like the familiar blue-green cyanobacteria, or maybe even a kind of purple microbe known as halobacteria. Either way, they used the sun's energy to convert CO2 and water into food, releasing oxygen as waste, which was okay for a while, but not for long. Because when these little microbes started farting out oxygen, it changed the chemical balance of the entire biosphere and eventually altered the face of our planet. First, within about 200 million years, the oxygen from these new bacteria began reacting with the iron in the oceans. This turned the ocean from a mellow green to a deep blood red as the seas began to fill with iron oxide, what we know as rust. In fact, you can still see exactly when and where this happened in strata known as banded iron formations, where huge swaths of rust settled out of the oceans to form layers of red-brown rock. But beyond making the water rusty, rising oxygen levels also shifted the balance of power among living things. Anaerobic microbes started to die off, as they were basically poisoned by the oxygen. Meanwhile, the newer, more efficient photosynthetic life began to spread. And things changed even more when the oxygen in the ocean left the water and entered the air. For the first time in Earth's history, large amounts of free oxygen started building up in the atmosphere. And this is what scientists call a game changer, because then the climate started to change too, drastically. As the photosynthetic bacteria kept spreading, they used up more and more of the carbon dioxide in the atmosphere, and CO2 is a greenhouse gas, so as its levels went down, so did the temperature. On top of that, oxygen also started reacting with the methane in the atmosphere, taking it out of circulation. With greenhouse gases at an all-time low, our planet started to see the first major ice ages in its history. Temperatures dropped so drastically that it triggered a global glaciation, and our once balmy water world became shrouded in ice. There may have been several pulses of these icy events, but by far the biggest of them came to be known as the Huronian glaciation, and it lasted for about 300 million years. Between these huge changes in climate and the radically different chemistry of the planet, most of life on Earth was pushed to the brink of extinction. And this included the new guys, the photosynthetic bacteria that were pumping out all the oxygen in the first place. Because remember, they needed CO2 to survive, so they were basically being suffocated by their own waste. Which, when I say it out loud, that's gotta be a terrible way to go. We don't know the full extent of the damage, but the effects of this whole episode, sometimes called the oxygen catastrophe, is considered one of the biggest extinction events in history. But you know how this movie ends, right? By the time the Huronian glacial period ended about 2.1 billion years ago, some life remained, and the life forms that survived inherited a better, more hospitable planet. Oxygen was now abundant in the air and water, and a new thing also appeared in the atmosphere, an ozone layer. This coating of molecular oxygen helped block dangerous ultraviolet radiation from the sun, and suddenly new things became possible. From there, well, you know what happens. Life became more complex and awesome and wonderful, and here we are. It seems strange that bacteria could end up covering the whole world in ice. And who'd have thought oxygen would be responsible for wiping out almost everybody? But it just goes to show you that sometimes things gotta get worse before they get better.
To the smartest human, to the most poisonous mushroom, to the tiniest bacterium, there is one thing that unites all living things on Earth, and that is the fact that all life is based on carbon chemistry. This element is so important, in fact, that it has its own branch of chemistry, organic chemistry. But carbon is not the most abundant element on Earth. That would be oxygen. And it is not the most stable, like helium. On the surface, it doesn't appear particularly special. Yet, if we look at our body composition, we find that carbon is everywhere in our cells. 20% of our body is made up of carbon, but it comprises less than 1% of the mass of the Earth's atmosphere, oceans, and crust. Why did life go to the trouble of concentrating carbon 20-fold in our bodies when other more abundant elements like oxygen and silicon were available, or even nitrogen, which makes up 78% of our atmosphere? The big question is why? We're going to examine that, and we're going to trace the logic that nature used in choosing this all-important element, carbon. That's coming up right now. 4 naturally occurring elements on the periodic table. Why is everything based on carbon and not something else when the choices are so many? The answer boils down to 3 things: complexity, abundance, and stability. What do I mean by this? Let's start with complexity. Carbon is able to form the complex molecular structures needed for the complex chemistry that life requires. Why is carbon able to do this? To understand this, we have to look at the foundation of chemistry, which is physics, particularly quantum mechanics. Quantum mechanics tells us that some electron orbital configurations are more energetically favorable than others, making them more stable. And the most stable configuration of electrons are those of the noble gases on the far right side of the periodic table. These are special elements that have a complete outer shell of electrons. This is the lowest energy configuration that an atom can have. This makes them chemically stable because they do not typically need to share, gain, or lose electrons to form bonds with other atoms to become more stable. This is also why they're chemically inert, since they do not generally interact with other atoms to form molecules. Why are only the noble gases this way and not other elements? Because they happen to have the right number of protons to have the right number of electrons to fill their shell fully. The driving force behind chemistry is really a hunt to get to the most energetically efficient state in a system, the state of lowest energy. And for the most part, this lowest energy state occurs when an atom is able to fill its outermost shell fully, like the noble elements. And some atoms can do this by sharing their electrons with other atoms to form what's called covalent chemical bonds. The periodic table of elements is arranged in such a way that we can easily tell by column the maximum number of bonds that an element can form with other elements. Starting from the left column of the table, the first group of atoms can form a maximum of 1 bond. The second column of elements can form 2 bonds. Third column, 3 bonds. This trend continues up to the fourth column, which can form 4 bonds. After this, the maximum number of bonds decreases. So the fifth column of elements can only form 3 maximum bonds. Then 2 bonds, 1 bond, and finally 0 bonds for the rightmost column, which are the noble elements, which are already the most stable. What you'll notice is that carbon is in the group of elements which can form the maximum number of bonds. It has a total of 6 electrons, 4 of which are on its outer shell. In order to fill its outermost shell, it needs 4 more electrons to make 8, like the noble gas neon. So it can share up to 4 additional electrons from other atoms to form covalent bonds, making it more stable. This makes carbon very versatile. Imagine if Lego bricks could be connected on 4 sides instead of 2. It would make building things easier. Each carbon atom can form a strong, stable bond with up to 4 other atoms, including other carbon atoms. This feature of carbon gives it the ability to form complex molecules, which is necessary for the complex chemical functions that life requires. Carbon-based molecules can form long, non-repetitive chains of polymers. They can form closed rings, and they can form single, double, or triple bonds with other elements. There are millions of possible configurations. Taken together, this makes carbon uniquely able to take part in a vast multitude of chemical processes. It can easily form long, stable polymer chains that can, for example, carry a lot of information. This is the case for DNA. DNA, after all, carries all the information that makes up living things, including us. And the 4 nucleotides that make up the building blocks of DNA are complex. Carbon is the backbone, partly because it can handle this complexity. The other elements are not as interesting. Take, for example, oxygen, which is the most abundant element on Earth. It can form only 2 bonds. This means that once it bonds with 2 other atoms, it's done. It can't really form interesting scaffolds of complex molecules, like carbon can. Boron could be interesting because it can form 3 bonds, so its molecular structures could also be fairly complex. The problem is that it's extremely rare, so it's just not very available for life to have chosen it as its backbone. This brings us to the second factor that made carbon attractive for life to latch onto: abundance. Not only is carbon versatile, it's also abundant. If we look at the top 5 most abundant elements in our solar system, what we will see is the following in order of abundance: hydrogen, helium, oxygen, carbon, and nitrogen. Now, if we look at the top 5 elements in our body, what we will see is the following in order of abundance: oxygen, carbon, hydrogen, nitrogen, and calcium. So what we see is that 4 out of the top 5 elements of the solar system are also among the top 5 elements making up the human body. This gives us another clue about why life is based on carbon. There's plenty of it in the universe. It's very abundant. It's easier to build something that you have a lot of. You can't build a castle if you don't have enough Lego bricks. At this point, you might say, if abundance is so important, then what about silicon, which is abundant and can also form 4 bonds? Or nitrogen, which can form only 3 bonds but makes up 78% of our atmosphere? This brings us to the third factor in determining the most suitable element that nature chose for life: stability. What I mean by this is bond stability. Let's look at that. As I said earlier, the structure of the periodic table is such that as a rule of thumb, all elements in each column have the same general properties. Carbon turns out to be the lightest element in the group of 14, or 4, depending on how you count. Therefore, we would expect that the sister elements, like silicon and germanium, would have similar chemical properties. Silicon is the next lightest element in the column. Its position on the periodic table tells us that, like carbon, it also has 4 valence electrons. This means it can also make 4 covalent bonds. For every molecule made out of carbon, there can be an analogous molecule with silicon in its place. Silicon also happens to be quite abundant on Earth. In fact, there's more silicon on Earth than carbon. It's just locked up in rocks within the Earth's crust. Chemically, silicon has 4 unpaired electrons in its outer orbital, just like carbon. The main difference is that silicon has its unpaired electrons farther away from its nucleus, on its 3rd shell, whereas carbon's electrons are on its 2nd shell, closer to the nucleus. This makes silicon's electrons more weakly bound to its nucleus. The consequence of this is that when silicon bonds with other atoms, including itself, the bonds formed are weaker and thus less stable. To give you some numbers, the silicon-silicon bond strength is 196. In contrast, carbon-carbon bonds are stronger at 334. This bond strength factor is also a reason nitrogen is not well suited to be the backbone of organic chemistry, as its bond strength is roughly half of carbon. You can't make a skyscraper with a foundation built from cardboard. The structural support has to be strong to hold the walls, windows, and doors. Organic molecules have the same need. The backbone has to be strong enough to withstand the conditions under which other parts of the molecule break their bonds and react chemically with other molecules. So the carbon-carbon scaffold needs to remain intact while the functional components break apart. A molecular scaffold made from nitrogen or silicon would more easily break apart. So if we go back now to the periodic table and look at the 3 rows of elements, if we remove all the chemically inert elements and then remove elements that can't form more than 2 bonds, then we remove all the elements that are exceedingly low in abundance, we end up with carbon, nitrogen, and silicon. Then, if we remove those that cannot form strong single bonds to themselves to create a strong molecular backbone, this leaves pretty much only carbon as the best choice. It is uniquely suited for life because of the best combination of abundance, ability to form complex structures, and stable bonds with other carbon atoms. Now, having said all that, there's nothing that would preclude silicon-based life forms from existing on an extraterrestrial planet if the conditions were right for it. By this logic, we can also imagine life based on germanium, tin, or even super-dense creatures made of lead. But we have to keep in mind that as elements get heavier, they tend to be more rare. So each of these is less plausible than the last. For example, germanium is at least 5 orders of magnitude less abundant than carbon, and tin is even rarer. It so happens that the pressures and temperatures on Earth work well for life forms that use liquid water as the solvent, and carbon-based molecules that can form a stable backbone on which biological chemistry can take place. If it gets too cold, water turns to ice and we'll have problems with chemical transport. If it gets too hot, we'll get issues with carbon polymer chains breaking too easily. We may never know for sure, but it's perfectly possible that carbon trumps everything else except in extreme environments. But we can't rule anything out, and we need to be open-minded about conditions in which life could hypothetically occur. For example, there are lakes of ethane and methane on Titan. Under the conditions of Titan, these are liquids. And like water on Earth, they could be used as a solvent by a different type of life form. So at different temperatures and pressures, it is conceivable that a different element may be more conducive to life. One of my Patreon supporters pointed out that we carbon life forms may right now be in the process of creating silicon artificial life forms. And this process is accelerating. This form of life could very likely exist in the near future, right here on Earth. But there's no evidence for life outside of Earth. It could be quite rare in the universe. So you can have all the various elements available in abundance, but the interactions or chemistry of these various elements is the critical process needed for life to happen. That process